Hello everyone and welcome to 30 days of DSA challenge, where we will be solving a DSA problem every day for the next 30 days. So this is our day number 15 and today we will solve a problem based on trees, and the level of this question is easy. The name of this question is binary tree in order traversal. So you will get this question link in description, and you can also download this Excel sheet from description. Now without wasting much time, let's see our question on LeetCode. So this is our question on LeetCode. The question statement is pretty short. It says, given the root of a binary tree, return the in-order traversal of its nodes value. The question simply says that, hey, I have given you a root of a binary tree, and just while doing a in-order traversal, give me the node values, right? Give me the nodes values. And here are some of the sample test cases. So before solving this problem, firstly, let's try to understand what is in-order traversal, and then we will solve this problem very easily, right? So let's say this is our binary tree and the root pointer is currently pointing to 1, right? Or you can say this 1 is nothing but our root node, right? And now we have to print the node values by doing a in-order traversal. So first let's understand what is in-order traversal. So as the name suggests, in-order traversal, right? In-order traversal. So what it is nothing but a traversal technique which is used to traverse our binary trees, right? And what does this in order says? It says firstly you need to cover the left sub part, right? You can say that you have to cover the left subtree. Then you have to print the value of the current node where you are standing, and after doing this you have to go and process the right sub part of the tree, right? So the in order traversal is pretty straightforward. It says first go and cover the leftmost part, the left sub part of the tree, correct? Then come back and print the current node value, right? And then go to the right sub part, right? Go and process the right sub part of the tree, correct? So this is the funda of in order traversal, you can say, right? So let's say currently I am standing at root, right? Let's say currently here I am standing at root. So what I have to do, first I need to go to the left part of the tree. So I'll come here at node number 2, right? So currently I'm standing here at node number 2, right? Again, what I have to do, I have to do the same thing. I need to go to the left part. So I'll go to the left part and then I will reach here at node number 4, right? So currently I am standing at node number 4. Again, what I have to do, I am doing an in order traversal. What it says firstly go and cover the left part. Okay, then I'll go to the left. But here at the left, you can say I have nothing. I have null. Now whenever I found null or I encounter null, what I have to do, I have to come back, because see, it is a null value. I cannot do anything. It is a null value, so I cannot also print the data, right? Because as it is null, what is the meaning of null? We have nothing here, right? So I will come back. I'll come back to my current node, right? I'll come back to the current node, which was node number 4, right? So for this node number 4, I have completed the left part, right? Now I have to print the node data, right? So what is the data? Data is nothing but 4. So I will print 4, right? And after printing that, what's next? Go to the right part. So now I'll go to the right part, right? And here you can also see at right, also I don't have anything, or you can say I have null. And whenever I encounter null, what I have to do, I have to go back. I have to return back, right? Because it is a null value, I cannot do anything with it, right? So I will go back to this 4, right? I will go back to this 4. Now for this node number 4, I have traversed its left part. I have printed the data of the node, and I have also traversed the right part, right? It means that I have done everything which I can do with this node number 4. That means I have completed everything. Now I can go to its parent, right? I can go to its parent. So from 4 I'll go to its parent, which is nothing but 2. So currently here I am standing at node number 2, right? Now again for the node number 2 we will follow the same thing. Go to the left, then print the data of the node, then go to the right, right? So see, if you clearly observe, then we have already traversed the left part, right? We have already traversed the left part for this node number 2, right? What's the next step? Print the node data, print the node data. So what is the data? Data is nothing but 2 itself, so we will print 2, right? Then what's the next step? Go to the right sub part, right? So now I'll go to the right part, right? Okay. So now currently I'm standing here at node number 5, So again, I'll do this 3 same things, right? I'll do it repeatedly. I'll go to the left, and at left I can see I have nothing, or I can say I have null, right? Whenever I encounter a null value, I have to return back. So I'll return back to the node itself. Right? And as I have covered the left part, now I am standing at the node, so I have to print the value of this node, right? And the value is nothing but 5. So I will print 5 here. Right? So left call is done. Printing the current node value is also done. Now I have to go to the right part. So now I'll go to the right part, right? But at the right part also you can clearly see that here I have nothing, or I have null, right? Whenever I encounter a null, I'll go back, or I'll return back to my root. Return back to my node, right? So now for this node number 5, I have traversed the left part, right? I have printed the data, and I have also covered the right part. It means that for this node number 5, I have done everything which I can do, right? I have visited the left part, I have printed the node's value, and I have also visited the right part. It means that I am done with this node, right? Okay. So when all the the left part, going to the left part, printing the node value, and going to the right part, when all these 3 things are done, what I have to do next? I have to go to its parent. So I'll go back at node number 2, right? Now I am standing here at node number 2. Now if you clearly observe, we have already visited the left part, we have printed this node value, and we have also visited the right part, right? It means that all the calls, or you can say I have done everything which I can do with this node number 2, right? I have went to its left part, I have printed the node value, I went to its right part as well. That means I have done whatever I can do with this node 2. I have done this, right? So now what we will do? Now we will go back to the parent of node number 2, right? Now we will go back to the parent of node number 2. And who is the parent of node number 2? The parent is nothing but root node, right? The parent is nothing but 1. So currently I am standing here at node 1, right? Now for this node 1, if you clearly observe, we have covered the left part, right? And once when we cover the left part, then what we have to do after covering left, we have to print the data, or we have to print the value of that particular node, right? So what's the value? Value is nothing but 1. So we will print 1, and then we will go to the right part. So now I will come to this right part, right? So now here I am standing at node number 3. Again, I will do the same thing. Firstly, I'll go to the left. So at left, I have null. Whenever I encounter null, what I have to do? I have to go back. To the node, right? Right? So now I am again standing here at node number 3. So once I cover the left part, and then I have to print the node value. So what is the value? Value is 3. So I will print it. And then I'll go to the right part. So at the right part also, I can see that here I have null value, right? Whenever I encounter null, what I have to do? I have to return back. So I will return back to here. I will return back to this node number 3, right? Now if you see, for this node number 3, we have covered the left part, we have printed the node value, and we have also covered the right part, right? That means for this node, we have done everything which we can do, right? We have covered the left, we have printed the node value, we have gone to the right part as well, right? So now what I'll do, I will go back, right? I will go back to its parent, right? And who is the parent of 3? So the parent of 3 is nothing but 1. Right? So now when I am standing here at node number 1, if you clearly observe, I have covered the left part, I have printed the value of this node, which is node 1, and I have also covered the right part, right? I have also covered the right part. Now for this particular node number 1, I have covered the left part, I have printed the data, I have covered the right part. Now what I'll do, I'll try to go to its parent, and the parent is nothing, or you can say null. So now here at this point, my traversal will be completed, and this will be my output, right? This will be my output, or you can say this will be my answer, or you can also say this will be our in order traversal. So this was our in order traversal, and while explaining the in order traversal, I have also explained you the algorithm which we are going to use to solve this particular problem. Okay, now let's think about how we are going to solve it by coding. Okay, so what we have to do, see, let's say currently I am standing here at node number 2, and this is nothing but node 7, and this is nothing but node 8, right? What we have to do, firstly we need to go to the left sub part, right? Then we need to print the node's value, and then we need to go to the right part, right? So we will take help of recursion, because see, repeatedly we are doing the same thing, we are repeatedly printing the left, we are repeatedly going to the left part, then printing the node, then going to the right part. We are doing it again and again. So let's use recursion, right? Okay, so let's say let me just write a function. So let's say this is our solve function, and it takes root and a vector known as answer, where we will store our in order traversal, right? Right? Okay, so let's say currently this is my root, and I am standing here at 2, right? What I have to do, I need to go to the left part, so I'll go to the left part, and now this will be my root, right? You can say, right? Now this will be my root. So what I'm doing, I'm going to the left part, and now how I can go to the left part using recursion? I can simply write solve root left, right? Solve root left and answer. So from this line, I will come here at node number 7, right? And this is my new root. Okay, again I need to go to the left, so I will again go to the left, and here I have null, right? Here I have null. So you can say now my root is pointing here, at null, right? And whenever in the example, while I was explaining you the in order traversal, I told you that whenever we are encountering any null value, we cannot do anything, so we have to return back, right? So let me just write it in our code. So if at any point my root is equal to null, if it is equal to null, then I do not need to do anything. I just need to return, or I just need to go back to the parent. Right? So from here I will go back to the parent, and now my root is again pointing to this 7, It means that for this 7 I have completed the left call, right? Okay, once I have completed the left call, what's next I have to do? I have to print the value of the node, right? So here we are using this answer variable to store the in order traversal, right? So now instead of printing, I will just store it into my answer, right? So I'll write answer dot push back root val, right? So from this line, whatever will be the value of that node, it will get stored into my answer variable, right? Into my answer vector, you can say. Okay, so for this 7, I have went to the left part and I found it null, so I returned back. Then I printed the node's value. Now where I need to go? Now I need to go to the right part. Right? So how I can do that with code? Very simple. I'll just write solve root right and answer, right? So I will come back, I will come here at this null, right? So firstly, let me just erase it. It is looking little clumsy. Okay, so now I am standing here at null and here is my root, right? So from this line, whenever my root is equal to null, I have to return back. So from here, I will return back to this root, right? I will return back to this node. So now my root will be pointing here at 7, right? Now for this 7, we have already covered the left part. We have already covered the right part. We have also printed the data. So what's next? go back to its parent, right? So now I will come back here at node number 2, and this will be my root, right? And for this node number 2, I have already covered the left part. So I just need to print the data. So from this line, the answer, sorry, you can say the value of the node will get saved into our answer vector, So right, for this node, I have traversed the left part, I have stored the node value, then I need to go to the right part, right? So from this particular line, I'll go to the right part, right? And again here at this node number 8, this will be my new root, and again these three things will get executed, right? So now I hope you have understood the approach, you have understood the recursive relation. Now let's think about the time complexity. So the time complexity is very simple. It is going to be O of n, where n is nothing but the total number of nodes, right? The total number of nodes into our binary tree. And if we talk about the space complexity, so here we are using our answer vector, which is storing all the node values. And how many nodes do we have? We have n number of nodes, right? So at max, the size of this answer variable will be equal to n, right? So you can say that the space complexity is going to be O of n plus we are using recursion, right? We are using recursion, and whenever we use recursion, we have a concept of recursive function call stack, right? So that recursive function call stack will also take some value, right? It will also take some space. So it will take total of O of n number of space, right? It will take total of O of n space. So I hope the approach is clear, the code is clear, the complexities are clear. Now let's fastly code it up on LeetCode. So now we are here on LeetCode. So let's fastly code the approach which we have just discussed. What we need one answer vector to store our inorder traversal, and at the end we will return our answer, right? So now I need to call my solve function. So at the solve function, I need to pass my root, and I also need to pass my answer vector, right? Now let's fastly implement our solve function. So here I will write void solve, and here I will write tree node asterisk root and vector of int, and I will pass it by reference, correct? So here I will firstly write my base case. If at any point root is equal to null, then go back, just get returned. And if this is not the case, then go to the left subpart. So here I will write root left, and I'll also pass my answer. And after coming back by traversing the left subpart, I need to store my answer. So here I will write answer dot push back root val, right? Whatever the value of the root, just store it into my answer, and then go to the right subpart. So here I will write solve root right, and I will also pass my answer, right? So this is the code. Let me just run this. Okay, so we have one error. So if root is equal to null, use of undeclared identifier. Okay, so here we have a typo. Here we need to write root ROOT. Okay, so now you can clearly see that all the sample test cases are running fine. Let me just submit this. So here you can clearly see that this solution is accepted, and I have also explained you the time and space complexities, and this was the recursive solution. But we also have one iterative solution which I also want to discuss in this video. So let's now discuss the iterative approach. So we know that in the previous approach we were using recursion, right? And due to this recursion, a function call stack was getting made, and due to this function call stack, an extra O of n space, right? An extra O of n space getting consumed, right? Now let me just visualize you how this function call stack was working, right? Let's see it. So firstly, let me just remove this. Okay, so see, when we started our recursion, we were here at the root, right? So in our function call stack, firstly we will have this one, right? Let's say we have one, right? Then what we did, we went to the left part here. So now my root is pointing here at node number 2. So in my function call stack, this node number 2 was stored, right? This 2 was stored, right? And after that, I again went to the left part. So now my root is pointing here at node number 4, right? So this 4 will again get stored into my function call stack, right? Into my function call stack. Okay. Now here from 4, I again try to go to the left part, which is equal to null, right? I again try to go to the left part, which was equal to null. And whenever I encountered a null value, right? Whenever I encountered a null value, what I did, I went back to the node and I printed the node, right? I printed the node. So you can say that in this function call stack, whatever is present at the top, I will print it. I will print it, right? I will print it. Correct? I will print it. So now if you clearly see, this 4, right? This 4 was entered into our function call stack at the end, or you can say at the last. And we took this 4, we took out this 4 at the first. So this is nothing but last in first out terminology, right? This is nothing but last in first out terminology. So our function call stack is behind the scene using this particular approach, that is last in first out. So this is the hint, right? This is the hint to solve this problem without using recursion. So see what recursion was doing. Recursion was behind the scenes using something like this, right? Something like this, not exactly this, something like this. And this was working on the property of last in first out. And do we have any data structure with the help of which we can perform this last in first out functionality? Yes, the answer is yes, and it is nothing but stack. So from here we got to understand that behind the scenes recursion was using something like stack, right? And I can also use stack by my own, right? I can also create my stack and I use it. So from here we got to know that yes, it is possible to solve this problem without using recursion by using stack, right? By using stack. Now we are going to use stack to solve this problem. Let's say this is our stack, which is initially empty, and currently we are pointing at the root node, right? We are pointing at the root node. Now what we need to do, we need to go to the left part, right? We need to go to the left part. So now I will go to the left part, right? I will go to the left part. But नहीं, इसको फिर से करते हैं. Okay, 1, 2, 3, start. Let's say this is our stack, which is currently empty, and right now my root is pointing here at node number 1, right? At node number 1. So what I need to do, firstly, let me just store this 1 into my stack. So I will store it into my stack, and then I will go to the left part. I will go to the left part, right? So now my root will point here at node number 2, right? My root will point here at node number 2. Again, I will do the same thing. I'll just store this 2. I'll just store this 2 into my stack. I'll store it into my stack, and then I'll go to the left part. I will go to the left part. So now my root will be pointing here at node 4, right? At node 4. So again, I'll do the same thing. I'll store 4 into my stack. And then I'll try to go to the left part. So at the left end, at the left part, you can clearly see that we have null, right? And here my root is pointing right now, right? My root is right now pointing at null. And as I discussed, whenever we are encountering a null, we need to go back to the node, and we need to print the data. Right? This is our stack. And at the top, which data, right? Which element we have? What we have? At the top, we have this 4. So we just need to store it inside my answer, right? We just need to store it inside my answer, and then I need to take it out from my stack. Right? I need to take it out from a stack. So I have covered the left part. I have covered the left portion for this node, which is nothing but 4. I have also printed the data, or you can say I have also printed the node data into my answer. I have added it into my answer. Now what I need to go to the right part, right? I need to go to the right part. So now I will try to go to right part, and at right also we have null, right? At right also we have null. So when I go to the right part, so my root is now pointing here at null, right? It is here pointing at null. Whenever we encounter null, what we have to do, we have to take out this data, and we need to add it into my Inorder Traversal answer, right? So I will add it here, I will take it out and I will add it, right? I will add it. So when I say I will take it out and I will add it, what does it mean? It means that for this node number 2, I have successfully completed the left traversal, right? I have successfully completed the left traversal. I have also printed this node data, and now I need to go to the right part, right? Now I need to go to the right part. So now what I will do, just suppose that my root is pointing here at node 2, right? Suppose that my root is pointing here at node 2. So we have covered the left part, we have printed the node data, and now we will go to the right part. Right? So at the right end we have this 5. So now suppose my root is pointing here, at 5, right? My root is pointing here at 5. So what I'll do, I'll store it into my stack, and then again I will try to go to its left part, right? I will again try to go its left part. So at the left, what we have? At the left, we have nothing but we have null, right? We have null. So now my root will point here at null, right? My root will point here at null. And whenever we encounter a null, what we have to do? We have to take the topmost element from my stack. So I'll just take it out, I'll just pop it out, and I will add it into my answer. Right? So now what we have done for this 5, right? For this 5, we went to the left part, we encountered null value, then we printed the node data, right? We added it into my answer. Now what's the next step? Next step is to go to the right of this node 5, right? Go to the right. So if I try to go to right, here also I have null, here also I have null, correct? Again, same thing. Whenever we encounter a null value, whatever we have to do, we have to come here at our stack. We have to see whichever element is present at the top. I will just pop it out. I will add it into my answer. Right? So now just think what we have done for this node number 5, right? What we have done for this node number 5. See, we have visited the left part and we encountered null, right? Then we printed the node value, which was 5, and then we tried to go to the right part. And the right part also was null. Then after doing that, what we did in our recursive solution, we came back to the root. So we reached here at 2. Now here for this 2 as well, we have covered the left part, we have printed the node value, we have covered the right part as well. Now what we'll do, we will go to its parent, right? Now here at node 1, for this node 1, what we have done. So firstly, let me just erase it. Yeah. For this node 1, we have already covered the left part, right? After covering the left part, what is the next task? The next task is to print the node value. So here, if you see, I have clearly printed the node value, right? Which is 1, right? So for this node number 1, I have covered the left part. I have printed the node value. Now what I need? Now I need to go to the right part, correct? Now I need to go to the right part, right? So now I will move to the right part, and here I will come here at node number 3, right? And now when I'm standing at node 3, what I'll do, I'll just store the value into my stack. So I'll store here 3. And for this node, I will go to its left part, right? So I'll go to the left, and here I will encounter a null value, and what we have discussed till now, whenever we are getting a null, just print out the data which is present into your stack. So we'll take this 3, we'll take out this 3, and we will add it into our answer. And after doing that, we will try to go to the right part, right? Because for this 3, we have covered the left part. Then we came back and we printed the data which was 3, and then we will go to the right part, right? Then we will go to the right part. So at right also we have null, right? At right part also we have null. Now whenever we encounter a null value, what we need to do, we need to look at into our stack, and whatever is present at the top of our stack, we will just add it into our answer. But if you clearly see into our stack, at this point our stack is empty, right? At this point our stack is empty. Now if you clearly see our stack is empty, and our root is pointing at null, right? Our root is pointing at null. What does this indicate? It indicates that we have covered all the nodes, right? We have covered all the nodes of our binary tree, and we have also successfully stored the in-order traversal, which is this 4, 2, 5, 1 and 3. Okay, so I hope this particular approach is also clear. Now let's think of how we will code it up. So now in order to code the approach which we have discussed, what do we need? We need a stack which will store the integer value. So let me name it as st, and we also need a vector, right? We also need a vector which will store integer values, and let me name it as answer, right? In this answer vector, I will store my in-order traversal, right? I'll store my in-order traversal, correct? Now what I need to do, I just need to check that if my root is not equal to null, right? If the root is not equal to null, so I will push the data, right? I will push the data. So instead of pushing the data, I can directly push the node. I can directly push this root node into my stack, right? So I'll directly push it into my stack. And after doing that, what I'll do, I'll again go to the left part. Right? So I will write I will write root is equal to roots left, right? This is what I will write for this if condition, right? And do I have to repeat this process? Do I need to repeat this process? So the answer is yes. Yes, I need to repeat it. Okay. Therefore, let me just write a while loop here. And we will think about the condition later, right? We'll think about the condition later. Okay. Now, if this is not the case, it means that if the root is equal to null, right? If it is equal to null, then what we have to do? If it is equal to null, then what we have to do? We have to take the topmost element which was present into our stack, right? So I will write st.top. This will give me the topmost element. I will store it into my root. Right? And then what I'll do st.pop. I will remove that node from my stack, and then I will put the value into my answer, right? So I'll write answer dot push back root val, right? Root val. Okay. And here this else condition will also get over, right? Now now just listen to me carefully. When we were doing a dry run, I told you that when the value of my root is equal to null and my stack is also empty, right? If these two conditions are matched, it indicates that we have successfully traversed all the nodes. And now we need to break out, right? We have successfully stored our answer, right? Okay, let's think how we can achieve these two conditions into our code, right? Okay, so see, in this particular line, if my root is not equal to null, then this if block of code will get executed, correct? When my code will come at this particular point, when it will come at else, yes, it will come at else when my root is equal to null, right? When my root is equal to null, right? What were the two conditions? The first one was when my root is equal to null, right? So this condition is satisfied, right? This condition is successfully satisfied. Okay. What's the second condition? That if my stack is empty, right? So what I can do, I can here directly write that if st.empty, it means that if my stack is empty, it means that I have successfully done the traversal. Then just come back, come out of this loop. So here I will write break. I will write a break condition. And now the code will get completed. But you may wondering, then what we will write here in this while loop? What we will write here in this while loop? So here we can write true, right? Here we can write true, right? Here we can write true, because when my root will be equal to null and my stack will be empty, I will automatically get out of this loop. I will automatically come out from this loop, right? And after coming out from this loop, I can just directly return my answer. Correct? So this is the iterative approach for solving this problem. And if we talk about the time complexity, then the time complexity is same, O of n. Why O of n? Because we are traversing the binary tree. So we are going at each node, and let's say the number of nodes is nothing but n. Therefore, the time complexity is O of n. Now, if we talk about the space complexity, then see what we are using. We are using one answer variable, answer vector, and what it will store? It will store all the node values. How many number of nodes we have? So we have n number of nodes, right? Therefore, the space complexity of this answer variable will be equal to O of n, right? Similarly, if we talk about this stack, right? If we talk about the space, how much space this stack will take. So you can say that at max it can take O of n, right? At max it can take O of n, right? It can take O of n. So here we can also write O of n, right? But see, one thing which I want to discuss, that here the space complexity of this stack will be equal to O of height of the tree, right? The height of the tree. And at max, there is a possibility that the height of the tree is equal to the value of n, right? Therefore, I have written O of n for the space complexity of this stack, okay? So I hope the time and space complexity is clear, the approach is clear, the code is clear. Now let's fastly code it up on LeetCode. And if you have doubt with this approach, then kindly do some dry runs, and then you will probably understand this approach as well. So now we are here on LeetCode. So what do we need? We need one answer vector to store our answer. And then we also need a stack of integer type. Let me name it as st, right? After that, what we need to do, we just need to write a while loop, and here I will write true, right? And at the end, I just need to return my answer variable or answer vector, right? So what I have to do here, firstly, I need to check that if my root is not equal to null, right? If my root is not equal to null, then what I have to do, I have to put this node into my stack, right? Put it into my stack. So instead of having int, what I'll write here, I can write tree node asterisk, right? So now this stack st will store nodes instead of the integer values, right? I hope it is clear. So here I will just directly write st dot push root, right? And then what I'll do, I'll go to the left part. So here I will write root is equal to roots left. Okay, I hope it is clear. Now if this is not the case, it means that if my root is equal to null, right? If it is pointing to null, then what I need, firstly I need to check a condition, that is my stack is empty, right? If the stack is empty, you can just break out, right? If the stack is empty and root is also pointing to null, it means that we have completed our traversal. So if this is the case, then we can break. If this is not the case, then what we need to do, then we can write root is equal to st dot top, then we will do st dot pop, and now I'll store my answer. So I'll write answer dot push back roots value, and after doing that we'll go to the right part, right? So here I will write root is equal to roots right. So this is the complete code for the iterative approach. I hope it is clear to you. Let me just run this. So here you can clearly see that all the 3 sample test cases are running fine. So let me just submit this. So here you can clearly see that this particular solution is also accepted, and I have already explained the time and space complexity. The time complexity of this solution is O of n, and the space complexity of this solution is also equal to O of n. But is it the most optimal solution? The answer is no. We also have one more approach which is known as Morris traversal, and with the help of Morris traversal, the time complexity will be same O of n, but the space complexity will get reduced to O of 1, that is constant space. But we will not discuss that approach in this video because already the length of this video is around 30 minutes. So we will discuss the Morris traversal in another video, and I hope this video was helpful to you. If it was, then make sure that you like this video, comment down your approach if you have a different approach, or if you are facing any problem while coding this solution, and make sure that you subscribe to this channel so that you get this type of content regularly. We will meet again tomorrow with a new question.